you are given n jobs. Each job has a start time, an end time, and a profit. Pick any subset of jobs so that their time ranges never overlap on an open interval. If one job ends exactly when another starts, that is allowed. Return the maximum total profit you can get from a compatible subset. Example 1 has 4 jobs on the timeline from 1 to 6. Job 0 runs from 1 to 3 with profit 50. Job 3 runs from 3 to 6 with profit 70. They only touch at time 3, so you may take both for a total of 120. Overlaps make naive brute force explode. Every subset is 2 to the n choices, which is impossible when n is 50,000. We need a clean decision at each job, take it or skip it, then reuse smaller answers. Package each job as one triple, start time, end time, and profit, and sort those whole rows by end time ascending. If 2 jobs share the same end, break ties by profit descending so the order stays deterministic. Then the time cursor moving forward only sees jobs that already finished, which is the direction DP walks. Watch the max of skip versus take. First job locks in 20. Second job compares carrying 20 against taking 10 on top of that 20. Third job is the fork in the road. Skip means keep the best plan that ends with job 1 only, which is 30. Take means pair job 2 with an earlier job that is already done before job 2 starts at time 3, job 1 still overlaps that window, so the only partner left is job 0 for 20, and 25 plus 20 beats 30, so 45 wins. If you take job 2, you need the best profit from an earlier job that is already finished before time 3. Binary search finds that match up quickly instead of scanning every earlier bar. When it points you at job 0, you add 25 to the 20 stored there. Here are 5 jobs in raw input order. Each row is start time, end time, and profit. Watch the bars before we reorder them. Sort by end time going up. When 2 jobs share the same end, put the higher profit first so the order is pinned. That is the order we fill the DP row underneath. To find the latest compatible earlier job, binary search on the sorted end times gives the predecessor index in logarithmic time per row instead of scanning every prior bar. Row 0 after sorting. Skip means take no job here, value 0. Take means grab this profit 8 with no earlier job that already finished, so 8 plus 0. The better of 0 and 8 is 8, so DP at 0 is 8. Row 1 starts at time 2. No earlier row ends at or before 2, so take is only its profit 2. Skip carries the running best 8 from the cell on the left. 8 beats 2, so DP at 1 stays 8. Row 2 starts at 4. Still no earlier end time on or before 4, so take is just its profit 1. Skip is still 8. 8 wins again, so DP at 2 is 8. Row 3 starts at 2 again. Same story, no earlier end fits before it start for a bundle, so take is 4 alone. Skip is 8. 8 still wins, so DP at 3 is 8. Last row starts at 8. Now there is a compatible earlier row, the long bar that ends at 8 already holds 8 in its DP cell. Take is 10 plus that 8, 18. Skip would keep 8. 18 wins, so DP at 4 is 18. In a full solution, binary search on the ends array would jump straight to that predecessor index instead of walking backward. The last cell reads 18, the maximum profit for this sample. N is the number of jobs. Time is order n log n, sorting by end time costs n log n, then one forward pass where each job does a binary search on earlier end times for log n work. Space is order n for the DP table and the sorted job rows. Main routine, 3 parallel arrays in, maximum profit out. Sort whole job rows by n time ascending, and when n's tie, by higher profit first. Copy n times into an array in that same sorted order for searching. N is how many sorted jobs we have. Allocate 1 dp cell per sorted position, all starting at 0. Walk I from the first sorted job to the last. Call the helper to find the best predecessor index among jobs strictly before I. Skip means carry the best profit from the previous index only. Take means add this job profit to the best compatible earlier cell when one exists. Store the better of skip and take at position I. The answer is the last dp value after processing every job. The helper binary searches indices 0 through I-1 on the sorted n times. If the middle job ends on or before start_I, we remember it and move low up to hunt for a later feasible predecessor, otherwise we shrink high. When the window collapses, return best or -1.